Close your eyes for a moment and imagine light. You probably picture something like sunlight streaming through a window, or maybe the warm glow of a lamp, perhaps the flash of a camera, or the flicker of a candle flame. Light seems simple. It seems obvious. It's the thing that lets us see. It's what fills the room when you flip a switch. It's what makes the sky blue and sunsets orange. It's everywhere. It's ordinary. But what if I told you that light is nothing like what you imagine? What if the thing you've seen every single day of your life, the thing you depend on for vision itself, is fundamentally stranger than almost anything else in the universe? What if light doesn't experience time? What if it has no perspective, no frame of reference, no journey from its point of view? What if asking what light sees is like asking what silence hears or what emptiness tastes? What if the speed of light isn't just a speed limit, but the fundamental structure of reality itself, woven into the fabric of space and time in ways that change everything we think we know about existence? Tonight, we're going to explore light, not as the familiar thing that brightens your day, but as one of the deepest mysteries physics has ever encountered. We'll move slowly. We'll start with what seems simple and let the strangeness reveal itself naturally, layer by layer, like peeling back the surface of reality to see the machinery underneath. By the end of this journey, you'll understand why light sits at the boundary between what we can know and what might be forever beyond comprehension. You'll see why physicists have spent over a century trying to understand something that seems so simple. And you'll discover that the universe is far stranger, far more beautiful, and far more mysterious than the everyday world suggests. And if you find yourself drifting off along the way, that's perfectly fine. Let the questions wash over you. Let the ideas settle gently into your mind like snow falling on a quiet landscape. There's no test, there's no rush, no deadline, just quiet curiosity and the gentle unfolding of one of nature's deepest secrets. Some of what we'll explore is established science, tested and verified thousands of times. Some of it ventures into speculation, into questions we haven't fully answered yet. I'll tell you which is which as we go. But all of it is rooted in real physics, in real experiments, in the actual structure of the universe as we've come to understand it, through centuries of careful observation and brilliant insight. So, settle in. Get comfortable. Let your mind relax into a state of gentle attention. We're about to explore something that's been hiding in plain sight your entire life. We're going to discover what light really is. Part 1. The first layer. Light in everyday life. Let's begin with something you've done 1,000 times. Something so ordinary you probably don't think about it at all. You're sitting in a dark room, maybe it's evening, and the sun has set. The room is filled with shadows. You can see vague shapes, the outline of furniture, but details are lost in darkness. You reach over and flip a light switch. The room brightens instantly. Suddenly everything is visible. Colors appear. Textures emerge. The world snaps into focus. You don't think about it. It just happens. Light appears. The room is illuminated. Simple. But let's slow that moment down. Let's watch what actually happens in that fraction of a second between the switch and the light. When you flip that switch, you complete an electrical circuit. Electrons begin flowing through wires, from a power source to the bulb. If it's an old incandescent bulb, the kind that's mostly been replaced by LED lights now, but that defined artificial light for over a century, those electrons flow through a thin tungsten filament inside the glass bulb. The filament is incredibly thin, thinner than a human hair, and it has high electrical resistance. When electrons try to flow through it, they encounter resistance, friction at the atomic level. This resistance converts electrical energy into heat. The filament gets hot, very hot, around 2,500 degrees Celsius. Hot enough to melt most metals. Hot enough to vaporize wood instantly. At this temperature, the tungsten begins to glow. The atoms in the filament are vibrating intensely, and this vibration causes them to emit electromagnetic radiation. At first, as the temperature rises, the radiation is mostly infrared, which we experience as heat. But as it gets hotter, the wavelength of the radiation shifts, moving into the visible spectrum. The filament begins to glow red, then orange, then yellow, then white, as it emits a broad spectrum of visible light. This light doesn't emerge all at once as a single beam. It radiates outward in all directions, in countless tiny packets of energy, each one traveling away from the filament at an incomprehensible speed. These packets are called photons. Each photon leaves the filament and travels across the room toward every surface. Some hit the walls and are absorbed, their energy converting to heat. Some hit the ceiling or the floor. Some bounce off reflective surfaces, changing direction. And some, a small fraction of the total, travel in a straight line from the filament to your eye. Let's say the bulb is 3 meters away from where you're sitting. Light travels at about 300 million meters per second. That means a photon crosses those 3 meters in about 10 billionths of a second. 1 divided by 100 million, a timescale so short that nothing in human experience comes close to it. 10 billionths of a second. Your neurons take about 5 thousandths of a second to fire. You blink in about 1/10th of a second. A heartbeat takes about 1 second. The photon completes its journey from bulb to eye in a time frame 100 million times shorter than a heartbeat. From your perspective, the light appears instantly. There's no perceptible delay. You flip the switch and the room is bright. Cause and effect happen so close together that they seem simultaneous. But here's the first strange thing, the first hint that light is not what it seems. From the photon's perspective, if it even has one, no time passes at all. The journey from the filament to your eye, those 3 meters and 10 billionths of a second from your point of view, don't exist for the photon. It is created and it is absorbed in the same instant. There is no in-between, no journey, no duration. The photon exists, but it doesn't experience existence the way you do. It doesn't age. It doesn't travel through time. It connects 2 points in space, the filament and your retina. But from its frame of reference, those points are the same point. The distance is 0. The time is 0. We'll come back to this strangeness. We'll explore what it means and why it happens. But for now, just hold on to this idea. Light does something that nothing else in your everyday experience does. It moves, but it doesn't age. It travels, but it doesn't experience duration. It crosses space, but from its perspective, there is no space to cross. This is our first clue that light is fundamentally different from ordinary matter, from ordinary experience, from the intuitive physics of the everyday world. But let's not get ahead of ourselves. Let's start with the basics and build from there step by step, letting each layer of understanding prepare us for the next. Let's start with the question that puzzled scientists for centuries. What is light? Part 2. Wave or particle. The first great mystery for most of human history, light, was simply a phenomenon, something that existed, that could be bright or dim, that came from the sun or from fire, but that didn't require explanation beyond that. It was part of the natural order of things, like air or water or heat. But as humans became more systematic in their observations, as we started doing what we now call science, light became a puzzle, a mystery that demanded explanation. Is light a substance? Is it a disturbance in some medium? Is it made of particles, like atoms? Or is it a wave, like sound or ripples on water? This question occupied some of the greatest minds in history, and the answer, when it finally emerged, was stranger than anyone expected. Let's start in the 1600s, with Isaac Newton. Newton is famous for his work on gravity, for his laws of motion, for inventing calculus, but he also spent enormous effort studying light. He was fascinated by it. He did experiments with prisms, showing that white light could be split into a spectrum of colors and then recombined into white light again. He studied reflection and refraction, the way light bounces off surfaces and bends when passing from one material to another. And based on his observations, Newton concluded that light must be made of particles, tiny corpuscles, he called them, traveling in straight lines at enormous speed. Light particles were emitted by luminous objects like the sun or a candle flame, traveled through space, and entered the eye, where they produced the sensation of vision. This made intuitive sense. Light traveled in straight lines. It cast sharp shadows. It could be reflected, like a ball bouncing off a wall. Particles behaved this way. Waves didn't, or at least not in the obvious ways. But there were problems with Newton's particle theory. Around the same time, a Dutch scientist named Christian Huygens was developing a different theory. Huygens proposed that light was a wave, not a wave of particles, but a wave in some kind of medium, a disturbance that propagated through space the way ripples propagate across a pond when you drop a stone into it. Huygens' wave theory could explain things that Newton's particle theory struggled with. For example, when light passed through a narrow opening, it didn't just create a sharp beam on the other side. It spread out slightly, creating a pattern of light and shadow that suggested the light was bending around the edges of the opening. This behavior, called diffraction, was characteristic of waves, not particles. But Huygens' theory had its own problems. If light was a wave, what was it a wave in? Sound waves are vibrations in air or water. Ocean waves are disturbances on the surface of water. What medium carried light waves? Huygens didn't have a good answer. He proposed the existence of an invisible, all-pervasive substance called the luminiferous ether, a hypothetical medium that filled all of space and transmitted light vibrations. But there was no evidence this ether existed. It was just a theoretical necessity. For over a century, these two theories competed: Newton's corpuscular theory and Huygens's wave theory. Both explained some observations but struggled with others. Both had brilliant advocates and serious weaknesses. Then, in the early 1800s, a series of experiments began to decisively favor the wave theory. The most famous of these was performed by an English scientist named Thomas Young in 1801. Young's experiment, now called the double-slit experiment, is one of the most important experiments in the history of science. It's elegant, simple, and its implications are profound. Here's what Young did. He took a light source, essentially a candle behind a narrow slit to create a thin beam of light. He then directed this beam at a barrier with two narrow slits cut into it, close together, parallel to each other. The light passed through both slits and then hit a screen on the other side. If light was made of particles, you'd expect to see two bright lines on the screen, one behind each slit, where the particles pass through. Maybe some scattering, some spreading, but basically two illuminated regions corresponding to the two slits. That's not what Young saw. Instead, the screen showed a pattern of multiple bright and dark bands. A central bright band, then a dark band, then another bright band, then another dark band, and so on, alternating across the screen. This pattern, called an interference pattern, was exactly what you'd expect if light was a wave. Here's why. When waves pass through two slits, they spread out from each slit in semicircular patterns, like ripples spreading from 2 points where stones hit the water. These spreading waves overlap. Where the peak of one wave meets the peak of another, they add together, creating a region of greater intensity. This is called constructive interference. Where the peak of one wave meets the trough of another, they cancel out, creating a region of zero intensity. This is called destructive interference. The alternating pattern of bright and dark bands that Young saw was exactly this. Constructive interference, creating bright bands where the waves from the two slits reinforced each other. Destructive interference, creating dark bands where they cancelled. Particles couldn't do this. You can't make darkness by adding light particles together. But waves could, and did. Young's experiment, along with similar work by other scientists, convinced the scientific community that light was a wave, not particles, waves. By the mid-1800s, this conclusion seemed unshakable. James Clerk Maxwell, one of the greatest physicists of the 19th century, developed a complete mathematical theory of electromagnetism that described light as electromagnetic waves, oscillating electric and magnetic fields, perpendicular to each other, propagating through space at a speed that Maxwell calculated to be about 300 million meters per second. This matched the measured speed of light exactly. It was a stunning confirmation. Light wasn't just similar to electromagnetic waves. It was electromagnetic waves. Visible light was just one small part of a vast electromagnetic spectrum that included radio waves, infrared radiation, ultraviolet light, X-rays, and more. The wave theory of light was triumphant. The case seemed closed. But then, at the very end of the 1800s and the beginning of the 1900s, new experiments began to reveal problems, cracks in the wave theory, phenomena that waves couldn't explain. And one of these problems would lead to a revolution in physics that would change everything. The problem was called the photoelectric effect. Here's what happened. Scientists discovered that when you shine light on certain metals, the light can knock electrons out of the metal's surface. This isn't surprising by itself. Light carries energy, and that energy could presumably shake electrons loose, the way ocean waves can wash sand off a beach. But the details were strange. You'd expect that brighter light, carrying more energy, would knock out more electrons, or would knock them out with more force. And you'd expect that dimmer light would knock out fewer electrons, or would knock them out more gently. That's not what happened. Instead, the number of electrons knocked out depended on the brightness of the light, which made sense. But the energy of each individual electron depended only on the color of the light, not its brightness. Blue light knocked out electrons with a certain amount of energy. Red light, even if it was incredibly bright, didn't knock out any electrons at all, or knocked them out with much less energy. This made no sense if light was purely a wave. A wave's energy depends on its amplitude, its height, not its frequency. A bigger wave carries more energy than a smaller wave of the same frequency. But in the photoelectric effect, the energy seemed to depend on frequency, which corresponds to color, and not on amplitude, which corresponds to brightness. It was as if light came in discrete packets, little bundles of energy, each bundle carrying an amount of energy that depended on the light's color. Blue light bundles carried more energy than red light bundles. A bright light had more bundles, but each bundle carried the same amount of energy as a dim light of the same color. In 1905, a young patent clerk named Albert Einstein published a paper explaining the photoelectric effect. It was one of 3 revolutionary papers he published that year. The other 2 were on Brownian motion and on what would become the special theory of relativity. 1905 was quite a year for Einstein. In the photoelectric effect paper, Einstein proposed that light was quantized. It came in discrete packets that he called light quanta. Each quantum carried an amount of energy proportional to the light's frequency. The higher the frequency, the more energy per quantum. The lower the frequency, the less energy per quantum. Blue light has a higher frequency than red light, so each blue light quantum carries more energy. A single blue quantum can knock an electron out of the metal with enough energy left over to give the electron some speed. A red quantum doesn't carry enough energy to knock out an electron at all, no matter how many red quanta you have. This explained the photoelectric effect perfectly. But it created a paradox. If light was quantized, if it came in discrete packets, then it behaved like particles. But Young's double-slit experiment and countless other observations showed that light behaved like waves. How could light be both? Einstein didn't call his light quantaphotons initially. That term came later, in 1926, coined by a chemist named Gilbert Lewis. But the concept was Einstein's. Light wasn't purely a wave. It was also, in some sense, made of particles. This was the beginning of quantum mechanics, though nobody knew it yet. And it would take another 20 years before physicists began to understand what wave-particle duality really meant. But the essential mystery was clear. Light was somehow both a wave and a particle. Both aspects were real. Both could be demonstrated experimentally. And somehow, impossibly, they coexisted. Let's explore how this can be. Part 3. The quantum nature of light. To understand how light can be both a wave and a particle, we need to enter the strange world of quantum mechanics. Quantum mechanics is the physics of the very small. It describes how atoms behave, how electrons orbit nuclei, how particles interact at scales far too tiny for us to see directly. And at these scales, the rules are different from the everyday rules we're familiar with. In the everyday world, things are either particles or waves. A baseball is a particle. It's located at a specific point in space. It has a definite trajectory. You can say where it is and where it's going. A sound wave is a wave. It's spread out over space. It interferes with other sound waves. It doesn't have a precise location. But in the quantum world, this distinction breaks down. Things can be both. They can have properties of particles and properties of waves simultaneously. This isn't just true of light. It's true of everything. Electrons, atoms, even molecules have wave-like properties. But light is where we first saw this clearly. And light remains the cleanest example of wave-particle duality, because light is pure quantum phenomenon. It has no mass. It exists only as vibrations in the electromagnetic field. Let's think carefully about what this duality means. When we say light is a wave, we're saying it has properties like wavelength, frequency, and the ability to interfere with itself. When light from two sources overlaps, it can create patterns of constructive and destructive interference, just like water waves or sound waves. When we say light is a particle, we're saying it comes in discrete units, photons. Each photon has a specific energy. Each photon is created at a specific event, like an electron dropping to a lower energy level in an atom. And each photon is absorbed at a specific event, like hitting a detector or entering your eye. But here's the crucial insight that quantum mechanics provides. The wave and the particle are not two separate things. They're two ways of describing the same thing, two different aspects of a single underlying reality. The wave describes the probability. The particle describes the outcome. Let me explain what that means. Imagine you have a single photon emitted from an atom. From the moment it's emitted until the moment it's absorbed, the photon is described by a wave function. This wave function is a mathematical object that encodes the probability of where the photon might be detected. The wave function can spread out over space. It can pass through two slits simultaneously. It can interfere with itself. In this sense, the photon is behaving like a wave. But when you actually detect the photon, when it hits a detector or a photographic plate or your retina, it doesn't arrive as a spread-out wave. It arrives at a single point, a single event, a particle-like interaction. The wave function collapses. The probability distribution becomes a definite outcome. This is the essence of quantum mechanics. Before measurement, particles are described by wave functions that encode probabilities. Upon measurement, the wave function collapses, and you get a definite result. This sounds abstract, so let's make it concrete with an example. Let's return to the double-slit experiment, but this time we'll do it with individual photons. Imagine you have a light source so dim that it emits only one photon at a time. One photon is created, travels across space, and is absorbed before the next photon is created. You point this source at a barrier with two slits, and behind the barrier you have a detector that can register individual photons. You turn on the light source and wait. Eventually, a photon is emitted. It travels toward the slits. What happens? If you think of the photon as a classical particle, you'd expect it to go through one slit or the other, not both. It's a single, indivisible thing. It can't split in half. But when you run this experiment, something strange happens. The first photon hits the detector at a seemingly random location. The second photon hits at a different random location. The third, the fourth, the fifth, all hitting at different spots that seem unrelated to each other. But if you keep the experiment running for hours, collecting thousands or millions of photons, a pattern emerges. The random dots build up into the same interference pattern you'd see if you used bright light, alternating bands of high and low probability. The pattern you'd get if waves were passing through both slits and interfering. But how? Each photon was emitted individually. Each photon is a single, discrete entity. How can a single photon create an interference pattern? The answer is that the photon, while traveling from source to detector, is described by a wave function that passes through both slits simultaneously. The wave function interferes with itself, and this interference determines the probability of where the photon will be detected. The photon doesn't go through one slit or the other. It goes through both, in a sense. Or, more precisely, the wave function that describes the photon's probability distribution passes through both slits. When the photon is finally detected, the wave function collapses and the photon appears at a single point. But which point is determined by the interference pattern of the wave function? This is wave-particle duality. The photon travels as a wave and arrives as a particle. The wave describes where it might go. The particle is where it actually goes. Now here's where it gets even stranger. What if you try to figure out which slit the photon went through? What if you put detectors at the slits to see whether the photon passes through the left slit or the right slit? When you do this, the interference pattern disappears. If you measure which slit the photon goes through, it goes through one slit, and you get a pattern on the final screen that looks like particles going through one slit or the other. No interference, no wave behavior. But if you don't measure which slit it goes through, you get interference. Wave behavior. The act of measurement changes the outcome. This is not a flaw in the experiment. It's not because our detectors are clumsy or disturb the photon too much. It's a fundamental feature of quantum mechanics. The photon behaves differently depending on whether you measure it. Before measurement, it's in a superposition state, described by a wave function that includes both possibilities, both slits. Upon measurement, it becomes definite. It went through one slit or the other. Measurement creates reality, in a sense. Or more carefully, measurement selects one outcome from a range of possibilities that were all equally real before the measurement. This is deeply weird, and it's been verified in thousands of experiments over the past century. It's not speculation. It's how the universe actually works at the quantum level. And light, because it's massless and exists purely as quantum phenomenon, shows this behavior more clearly than almost anything else. But this raises profound questions. Questions that physicists and philosophers are still grappling with. What is measurement? What counts as an observation? Does the universe really exist in a fuzzy, indefinite state until someone looks at it? Or is there something deeper happening that we don't understand? These questions are part of what's called the measurement problem in quantum mechanics, and we don't have final answers. Different interpretations of quantum mechanics give different answers. Some interpretations say that measurement is special, that consciousness somehow collapses the wave function. Other interpretations say that the wave function never collapses, that all possible outcomes occur in parallel universes, and measurement just determines which universe you experience. Still, other interpretations deny that wave functions are real at all and say they're just mathematical tools for predicting probabilities. We won't resolve these debates here. Professional physicists haven't resolved them in 100 years. But the important point is this: light is not a wave or a particle. It's something more fundamental, something that has both wave-like and particle-like properties, depending on how you interact with it. And this duality is not a limitation of our understanding. It's the nature of reality at the quantum level. Let's sit with this for a moment. Let's let it settle. We've learned that light is both a wave and a particle, that it travels as a probability distribution and arrives as a definite event, that the act of measurement affects the outcome in fundamental ways. This is strange, deeply strange. It violates our intuition about how the world should work. But it's true, and it's not just an abstract theoretical curiosity. It's the foundation of modern technology. Lasers work because of the quantum nature of light. Solar panels work because of the photoelectric effect. Quantum computers, which are just starting to become practical, work by harnessing the wave-like properties of particles to perform calculations that classical computers can't. The strangeness of light is not just philosophically interesting, it's practically important. Now let's turn to another question, another piece of the puzzle. Why does light have no mass? And what does that mean? Part 4. The masslessness of light. Mass is one of the fundamental properties of matter. It's a measure of how much stuff something contains, how much resistance it has to being accelerated, how much gravitational pull it exerts and experiences. A rock has mass. An atom has mass. Even the lightest known particles, neutrinos, have a tiny amount of mass. But photons, the particles of light, have no mass at all. Zero. Exactly zero. Not very little mass, or almost no mass. Literally zero. This might seem like a technicality, like just another property of light that doesn't really matter. But it's not. The masslessness of photons is absolutely fundamental. It's what allows light to move at the speed of light. It's what requires light to move at the speed of light. And it's what makes light so different from ordinary matter. Let's understand why. In Einstein's theory of relativity, mass and energy are related. They're two aspects of the same thing. The famous equation E equals mc squared tells us that mass can be converted to energy, and energy can manifest as mass. But there's a subtlety here. When we talk about mass in relativity, we usually mean rest mass. The mass something has when it's not moving. A rock sitting on the ground has rest mass. An electron sitting in an atom has rest mass. That when something moves, it gains kinetic energy, the energy of motion. And according to relativity, this energy contributes to the thing's total mass. The faster it moves, the more energy it has, and the more massive it becomes. This effect is tiny at everyday speeds. A car moving at 60 miles per hour gains an incredibly small amount of mass, far too small to measure. But as you approach the speed of light, the effect becomes dramatic. At 50% of the speed of light, an object's total mass increases by about 15%. At 90% of light speed, it increases by a factor of about 2.3. At 99%, about 7 times. At 99.9%, about 22 times. As you get closer and closer to the speed of light, the mass increase grows without bound. At exactly the speed of light, for something with any rest mass at all, the total mass would be infinite. This means that accelerating something with rest mass to the speed of light would require infinite energy. It's impossible. You can get arbitrarily close, but you can never quite reach it. This is why we say that the speed of light is the universal speed limit. Nothing with mass can travel at the speed of light. But photons have no rest mass, zero. So this restriction doesn't apply to them. For a photon, Moving at the speed of light doesn't require infinite energy because there's no rest mass to accelerate. The photon is born moving at light speed. It doesn't need to accelerate to that speed. It can't move slower. It can't stop. From the moment a photon is created, whether in a nuclear reaction in the core of the sun, or in the vibration of an electron in a light bulb filament, or in the annihilation of matter and antimatter, it moves at exactly 299,792,458 meters per second in a vacuum. This speed is universal. It's the same for all photons, regardless of their energy or frequency. Red light and blue light and gamma rays all travel at the same speed in a vacuum. This number, the speed of light, is so important in physics that it's given its own symbol, usually written as the letter C. It appears in countless equations, in relativity, in electromagnetism, in quantum mechanics. It's woven into the mathematical structure of the universe. But why this particular speed? Why 299,792,458 meters per second and not some other number? The answer is that the speed itself is arbitrary, depending on what units you use to measure distance and time. If we use different units, the number would be different. What's not arbitrary is that this speed is the maximum speed at which information can travel, the speed at which massless particles must move, and the ratio between space and time in the structure of space-time. The speed of light is not just a property of light, it's a property of the universe. To understand this, we need to think about what mass really is, and why photons don't have it. In particle physics, most particles get their mass from something called the Higgs field. This is a quantum field that permeates all of space, similar to the electromagnetic field. Particles that interact with the Higgs field experience resistance when they try to move, and this resistance manifests as mass. It's a bit like moving through molasses. The molasses doesn't make you heavier in the sense of gravitational pull, but it makes you harder to accelerate, which is what mass does. Different particles interact with the Higgs field with different strengths. Electrons interact weakly, so they have relatively little mass. Quarks, the particles that make up protons and neutrons, interact more strongly, so they have more mass. Top quarks interact very strongly, so they're very massive. But photons don't interact with the Higgs field at all. They pass through it without resistance. They have no rest mass. This is not a coincidence. Photons are excitations of the electromagnetic field, and the structure of electromagnetism requires that photons be massless. If photons had mass, even a tiny amount, electromagnetism would work differently. Electric fields would behave differently over long distances. Magnetic fields would have different properties. The equations of electromagnetism, Maxwell's equations, assume that light travels at a specific speed in a vacuum, and this assumption requires photons to be massless. So the masslessness of photons is not an accident. It's a necessary consequence of the way electromagnetism works, the way the electromagnetic field is structured, the way photons couple to charged particles. And this masslessness has profound consequences. It means photons always move at light speed, never faster, never slower. They're created moving at light speed, and they're absorbed while moving at light speed. They don't accelerate, they don't decelerate. They don't experience forces that change their speed, only forces that change their direction or energy. It also means photons are fundamentally different from matter. Matter is made of particles with mass. Electrons, quarks, atoms. These particles can be at rest. They can move at various speeds. They can be accelerated and slowed down. Photons can't. They exist only in motion, only at light speed. This leads to our next strange property of light. If photons are always moving at light speed, and if at light speed time stops, then photons don't experience time. Let's explore what this means. Part 5. Light and the nature of time. Time is one of the most fundamental aspects of our experience. We live in time. We remember the past, experience the present, and anticipate the future. Moments pass. We age. Things change. Time flows, or seems to, in one direction from past to future, irreversibly. But time is stranger than it seems. Einstein's theory of relativity revealed that time is not absolute. It's not the same for everyone. It depends on how fast you're moving and how strong the gravitational field is where you are. This is called time dilation, and it's been measured and verified in countless experiments. For example, if you put an extremely precise atomic clock on an airplane and fly it around the world, when you bring it back and compare it to an identical clock that stayed on the ground, the traveling clock will show slightly less time has passed. It will be behind by a few billionths of a second. This isn't because the vibrations of the atoms in the clock were affected by the motion. It's because time itself passed more slowly for the moving clock. The effect is tiny at airplane speeds, but it's real and measurable. The faster you go, the more dramatic the effect becomes. At a significant fraction of the speed of light, the time dilation becomes very noticeable. Imagine you have a twin. Your twin gets on a spaceship and travels at 90% of the speed of light to a star system 10 light years away, then turns around and comes back. From your perspective on Earth, the round trip takes about 22 years. Your twin is gone for 22 years. But from your twin's perspective, experiencing time on the ship, only about 10 years pass. Your twin ages 10 years while you age 22 years. When your twin returns, they're 12 years younger than you. This is not science fiction. This is what relativity predicts, and every experiment we've done confirms it. Time passes at different rates depending on your velocity. The closer you get to the speed of light, the more extreme the effect. At 99% of light speed, time slows by a factor of about 7. At 99.99%, a factor of about 70. And at exactly the speed of light, for a massless particle like a photon, time stops completely. From the photon's perspective, no time passes between when it's emitted and when it's absorbed. The journey, no matter how long from our perspective, takes zero time from the photon's perspective. Let me emphasize this, because it's so counterintuitive. A photon emitted from the sun takes about 8 minutes to reach Earth, from our perspective. But from the photon's perspective, it's emitted from the sun and absorbed by your eye in the same instant. No time passes. A photon from a distant star, traveling for thousands or millions or billions of years across space before reaching a telescope on Earth, experiences zero time. It's created in a fusion reaction in the core of that distant star and absorbed by a detector in the telescope in the same timeless instant. A photon from the most distant galaxy we can observe, traveling for over 13 billion years, spanning most of the history of the universe, experiences no duration whatsoever. This is what it means for time to stop at the speed of light. But it's even stranger than that. It's not just that time passes very slowly for photons. It's that the concept of time doesn't apply to photons in the way it applies to us. In relativity, we describe events using something called a space-time diagram. Imagine a graph where one axis represents space and another represents time. Every event, everything that happens, is a point on this diagram. The path an object takes through space-time is called its world line. For a person sitting still, their world line is a vertical line, going up the time axis. They're staying at the same location in space while moving forward in time. For a person walking, their world line is tilted, representing movement through both space and time. For something moving very fast, the world line tilts more steeply, approaching a 45-degree angle, which represents motion at the speed of light. And for a photon, moving at exactly the speed of light, the world line is exactly at this 45-degree angle. But here's the strange part. From the photon's perspective, this world line has zero length, The space-time interval between emission and absorption is zero. This is hard to visualize because it contradicts our intuition. How can something travel across space but have zero space-time interval? The answer is that space and time trade off against each other in a specific way in relativity. As you move faster through space, you move slower through time. At the speed of light, you move through space at maximum rate and through time at zero rate. For a photon, all points along its path are, in a sense, the same point. The distance is zero. The time is zero. The journey doesn't exist from the photon's frame of reference. This is why we sometimes say that photons don't have a valid reference frame. You can't construct a consistent description of the universe from a photon's perspective because the mathematics breaks down. Distances shrink to zero. Times shrink to zero. The concept of perspective itself becomes meaningless. Light exists, but it doesn't experience existence. Now, this raises a fascinating philosophical question. If photons don't experience time, what does that mean for the nature of time itself? Is time real? Or is it just a perspective, something that emerges from certain kinds of motion, but that doesn't apply universally? This question touches on deep debates in physics and philosophy. Let me outline some of the perspectives. One view, associated with Einstein and many modern physicists, is called the block universe, or eternalist view. According to this view, all of time exists simultaneously. The past, present, and future are all equally real. They're all part of a four-dimensional structure called space-time, where time is just another dimension like space. From this perspective, the flow of time, the feeling that moments pass, and that the present moment is special, is an illusion. It's a subjective experience arising from the way conscious beings process information, but it doesn't reflect fundamental reality. The entire history of the universe, from the Big Bang to the far future, exists as a single, eternal, unchanging structure. Your birth and your death, and every moment in between, are all equally real, all existing as different points in space-time. This view is supported by relativity, which says there's no universal now, no present moment, that all observers agree on. What's now for you might be the past or future for someone moving at a different speed. If there's no universal present, then the distinction between past, present, and future is observer-dependent, which suggests that all moments exist equally. But many people find this view unsatisfying or even disturbing. It seems to deny free will, to suggest that the future is fixed, that everything that will happen has already happened in some timeless sense. An alternative view, called presentism, says that only the present moment is real. The past no longer exists. The future doesn't exist yet. Reality is constantly coming into being, moment by moment. This view aligns better with our subjective experience of time flowing, but it's harder to reconcile with relativity, which seems to require that past and future events be as real as present events. There are other views as well, and the debate continues. But here's where light becomes relevant to this debate. Light, moving at the speed of light, connects events that are separated in time from our perspective, but that are simultaneous from the light's perspective. If you think of time as something objective, something that applies to the entire universe, then the fact that photons don't experience time is just a curiosity, a consequence of their speed. But if you think of time as perspective-dependent, as something that emerges from the way different observers move through space-time, then photons are objects that exist outside of time. They're connections in space-time that don't have duration from any internal perspective. In this view, photons are more fundamental than time. They're the threads that connect events, defining causal relationships, but they themselves exist in a timeless state. This is speculation, to be clear. We don't know the ultimate nature of time. We don't know if the block universe view, or presentism, or some other view is correct. But light, in its timelessness, in its existence at the boundary of what can experience time and what can't, gives us a window into these deep questions. Let's pause here and take a breath. We've covered a lot of ground. We've explored wave-particle duality, the masslessness of photons, and the strange fact that light doesn't experience time. These aren't easy ideas. They're counterintuitive. They challenge our everyday understanding of reality. But they're true. They're confirmed by experiment after experiment. They're part of the structure of the universe. And we're not done yet. There's more strangeness to explore. Let's ask another question, one that might seem nonsensical at first, but that leads to profound insights. What does light see? Part 6. What does light see? When we ask what light sees, we're not asking whether photons have eyes or consciousness. Obviously, they don't. They're not alive. They're not aware. But the question has a real meaning in physics. We're asking, from the perspective of a photon, what is the structure of space and time? What does the universe look like from the point of view of something moving at the speed of light? We've already established that from a photon's perspective, no time passes. The photon is emitted and absorbed in the same instant. But what about space? What about the distances the photon crosses? In relativity, there's a phenomenon called length contraction. Objects moving at high speeds appear shortened in the direction of motion from the perspective of a stationary observer. This is a real effect, not an optical illusion. It's a consequence of the way space and time are related in space-time. The faster something moves, the more it's contracted. At 90% of light speed, lengths are contracted by about 55%, at 99% by about 86%, and at exactly the speed of light, lengths are contracted to zero. From a photon's perspective, the distance between where it's emitted and where it's absorbed is zero. The entire journey, no matter how far from our perspective, is compressed to a single point. So not only does the photon experience no time, it also experiences no space. The universe, from its perspective, is collapsed to a point. This is hard to wrap your mind around. How can something travel across billions of light years of space, but experience zero distance? The answer is that distance, like time, is not absolute. It depends on your reference frame, on how fast you're moving. From our perspective, sitting relatively still, the universe is vast. Galaxies are separated by millions or billions of light years. The observable universe is about 93 billion light years across. But from the perspective of a photon crossing the observable universe, the entire journey is instantaneous and covers zero distance. Both perspectives are valid. Both are real. Reality depends on the observer. This is the heart of relativity. Space and time are not fixed, absolute arenas in which events occur. They're flexible, observer-dependent properties of space-time and light, moving at the boundary of space-time, moving at the speed that defines the relationship between space and time. Experience is the most extreme version of this observer dependence. Now, I said earlier that you can't really construct a valid reference frame for a photon. The mathematics of relativity breaks down at exactly the speed of light. So when I say, from the photon's perspective, I'm using a shorthand, a way of talking about the limit as you approach light speed. But that limit is informative. It tells us something real about the nature of light and the structure of space-time. Light exists at the boundary. It's the thing that defines the limit. And at that limit, space and time become meaningless in a certain sense. This raises another question. If photons don't experience space or time, what do they experience? Is there any sense in which a photon has a perspective or a journey? The answer is no. Not in the way we think about perspectives and journeys. A photon is created in one event and absorbed in another event. From our perspective, these events are separated by space and time. The photon travels from one to the other. But from any perspective associated with the photon, there's no separation. The events are the same event. The photon doesn't have a history, a trajectory, a journey. It simply connects two points in space-time. This is why we sometimes say that photons are timeless, or that they exist outside of time. It's not poetic language. It's a literal description of their relationship to space-time. And this timelessness has implications for how we think about the universe. Consider the cosmic microwave background, the faint glow of radiation left over from the Big Bang. This radiation has been traveling through space for over 13 billion years, from our perspective. It was emitted when the universe was only about 380,000 years old, when atoms first formed, and the universe became transparent to light. These photons have been traveling ever since, gradually cooling and stretching as the universe expands, until they reach our detectors today. But from the perspective of those photons, no time has passed. They were emitted in the early universe and absorbed by our detectors in the same timeless instant. Every observation we make with light is, in a sense, a connection across time. A photon links the event that created it to the event that absorbs it, creating a causal thread through spacetime. And the photon itself exists in a timeless state, connecting past to present instantaneously from its own perspective. This is what we mean when we say light doesn't see anything. It doesn't have a perspective. It is the connection that allows perspectives to exist, but it doesn't participate in perspective itself. Light is the boundary, the limit, the thread that weaves space-time together. Now let's consider what this means for the largest scales of the universe. Part 7. Light and the Cosmic Horizon. The universe is big, unimaginably big, and it's getting bigger. The current best estimate is that the observable universe, the part we can see, extends about 46.5 billion light-years in every direction from Earth. That's a sphere with a diameter of about 93 billion light-years. But wait, if the universe is only about 13.8 billion years old, how can we see things that are more than 13.8 billion light-years away? Shouldn't the farthest thing we can see be 13.8 billion light-years away, since that's the distance light could have traveled since the Big Bang? The answer is that the universe is expanding. Space itself is stretching. When light was emitted from distant galaxies billions of years ago, those galaxies were much closer than they are now. The light has been traveling through expanding space, and in the time it's been traveling, the space between us and those galaxies has expanded dramatically. So the galaxies that emitted light 13 billion years ago are now much farther than 13 billion light-years away. They're now about 46 billion light-years away, because space has been expanding the whole time the light was traveling. This expansion is accelerating, driven by something called dark energy, a mysterious component of the universe that we don't fully understand, but that seems to make up about 70% of the universe's total energy. Because the expansion is accelerating, there are galaxies so far away that their light will never reach us, not because the light isn't traveling toward us, but because the space between us is expanding faster than light can cross it. Think of it like being on a treadmill. You're walking forward at a steady pace, but the treadmill is accelerating. At first, you make progress, but eventually, the treadmill is moving backward faster than you can walk forward. You're still walking, but you're getting farther from the front of the treadmill, not closer. This is what's happening with the most distant galaxies. They're emitting light toward us, but the space between us is expanding faster than the light can cover the distance. These galaxies are receding faster than light. This doesn't violate relativity. Nothing is moving through space faster than light. The galaxies aren't moving through space at all, really. The space itself is expanding, carrying the galaxies with it. But the result is that there's a boundary, called the cosmic horizon, beyond which we can never receive light. Beyond this horizon, there are galaxies, stars, planets, perhaps civilizations, but we can't see them. We can't ever see them. Their light will never reach us. From our perspective, those galaxies are beyond the edge of the knowable universe. But from a photon's perspective, there is no horizon, there is no distance. All points in space-time are connected instantaneously. The cosmic horizon is an artifact of perspective, of the fact that we experience time and that space is expanding. For us, some things are too far for light to reach, but for light itself, distance doesn't exist. This creates a strange asymmetry. Light connects events across space and time from our perspective, but experiences no separation from its own perspective. The universe, as experienced by photons, is fundamentally different from the universe as experienced by massive particles, by objects that move slower than light and that experience the flow of time. And this difference reveals something profound about the structure of reality. Reality is not a single objective thing that's the same for all observers. Reality depends on perspective, on motion, on the observer's relationship to space-time. For us, the universe is vast and ancient. For photons, it's collapsed and timeless. Both descriptions are true. Both are aspects of the same underlying structure. This is the lesson of relativity. The universe doesn't have a single privileged description. It has many descriptions, one for each possible observer, and all of them are equally valid. Light, because it moves at the boundary of space-time, shows us the most extreme version of this observer dependence. Now let's explore another consequence of light's special nature. The fact that light is the fastest thing in the universe, the cosmic speed limit, has implications for causality, for the relationship between cause and effect. Part 8. Light and causality. Causality is the principle that causes precede effects. If event A causes event B, then A must happen before B. This seems obvious, fundamental to how we understand the world. But relativity complicates this picture. In relativity, the order of events can depend on the observer. Two events that happen at the same time from one observer's perspective might happen at different times from another observer's perspective. One observer might see event A happen first, while another observer sees event B happen first. This seems to violate causality. How can the order of cause and effect depend on the observer? The answer is that it can't, at least not for events that are causally connected. And light is what protects causality. Here's how it works. In space-time, every event has something called a light cone. Imagine an event occurring at a specific point in space and time. Now imagine light spreading out from that event in all directions at the speed of light. The path this light takes through space-time forms a cone-shaped surface. Everything inside the future light cone can be affected by the event. These are events that are close enough in space and time that a signal traveling at light speed or slower can reach them. Everything inside the past light cone could have affected the event. These are events from which a signal traveling at light speed or slower could have reached the original event. Everything outside both light cones cannot be causally connected to the event. They're too far away in space for any signal traveling at or below light speed to connect them. Now here's the crucial point. For events inside each other's light cones, all observers agree on the order. If event A is inside event B's past light cone, then all observers, no matter how fast they're moving, will agree that A happened before B. The order is unambiguous. Causality is preserved. But for events outside each other's light cones, the order can depend on the observer. Different observers can disagree about which happened first. But this doesn't matter for causality, because these events can't affect each other anyway. They're too far apart in space and time for any causal influence to travel between them. Light, moving at the speed of light, defines the boundary of causality. It separates events that can influence each other from events that can't. This is why the speed of light is so fundamental. It's not just a property of light. It's the speed limit for causality, for information, for any influence whatsoever. Nothing can travel faster than light, because if it could, It could create causal paradoxes. It could send signals backward in time, allowing effects to precede causes, creating logical contradictions. The universe doesn't allow this. The structure of space-time enforces the speed limit, and light, being massless, naturally travels at this limiting speed. So when we ask what light sees, part of the answer is that light defines what it means for events to be connected, for causes to lead to effects, for information to flow from one place to another. Light is the messenger of the universe. It's the fastest possible messenger, and it defines the boundaries of what can communicate with what. Every photon that reaches your eye carries information from the event that emitted it. That photon creates a causal link between the emission event and the absorption event in your retina. And that link is the fastest possible link. Nothing could have carried that information more quickly. When you look at the stars, you're receiving messages from the past. Photons that were emitted years or centuries or millennia ago, carrying information about what those stars were like when the photons were emitted. The universe communicates with itself through light, and the speed of that communication defines the structure of causality, the relationship between past, present, and future, the limits of what can know about what. This is another sense in which light is fundamental. It's not just a phenomenon we observe, it's part of the machinery of space-time itself. Now let's consider what happens to light in extreme conditions, in the strongest gravitational fields we know of. What happens to light near a black hole? Part 9. Light and black holes. Black holes are regions of spacetime where gravity is so strong that nothing, not even light, can escape. This is the definition of a black hole. The boundary beyond which escape is impossible is called the event horizon. Black holes form when massive stars collapse at the end of their lives, or when enormous amounts of matter accumulate and compress beyond a critical density. Once the event horizon forms, anything that crosses it is trapped forever. It falls inexorably toward the center, toward the singularity, the point of infinite density. For our purposes, the interesting thing about black holes is how they affect light. Near a black hole, space-time is curved dramatically. Gravity, in Einstein's general relativity, is not a force in the traditional sense. It's a curvature of space-time, caused by mass and energy. Objects move along the straightest possible paths in this curved space-time, and those paths appear curved to distant observers. Light, being massless, also follows paths in curved space-time. These paths are called null geodesics. They're the straightest possible paths for something moving at the speed of light. But near a black hole, space-time is so curved that light paths bend dramatically. If you shine a beam of light near but not directly toward a black hole, the light will curve around the black hole. From a distance, it looks like the black hole's gravity is pulling the light, bending its path. The closer the light passes to the black hole, the more it bends. At a certain distance, called the photon sphere, light can orbit the black hole. A photon traveling tangent to the photon sphere will circle the black hole forever, trapped in a closed orbit. This is unstable, though. Any slight perturbation, and the photon either spirals inward, crossing the event horizon and falling into the black hole, or spirals outward, escaping to infinity. For light that crosses the event horizon, there's no escape. Once inside, all paths, even light paths, lead toward the singularity. Light emitted from inside the event horizon never reaches the outside universe. It's trapped, absorbed, lost. This is why black holes are black. They don't emit light. Any light that gets close enough to cross the event horizon can't escape to be seen. But there's a subtlety here related to what we've learned about light's timelessness. From the perspective of a photon falling into a black hole, no time passes. The photon crosses the event horizon and reaches the singularity in the same instant, from its perspective. But from the perspective of a distant observer, watching the photon fall, something strange happens. As the photon approaches the event horizon, time dilation becomes extreme. Time passes more slowly near the event horizon because of the intense gravity. From the distant observer's perspective, the photon appears to slow down as it approaches the horizon. It takes longer and longer to cover each increment of distance. The photon's light becomes more and more redshifted, stretched to longer wavelengths, dimmer and dimmer. Asymptotically, the photon appears to freeze just at the event horizon, never quite crossing, fading to infinite redshift and becoming undetectable. But this is just an artifact of the distant observer's perspective. From the photon's perspective, and from the perspective of anyone falling alongside the photon, the crossing happens in finite time. The photon does cross the horizon and does reach the singularity. It's just that signals about this crossing can never reach the distant observer. The event horizon is a one-way membrane for information. This creates a fascinating situation. The photon, from its own timeless perspective, is emitted and absorbed at the singularity in the same instant. From the perspective of a distant observer, the photon never quite reaches the horizon, fading asymptotically over infinite time. Both perspectives are describing the same events, but the descriptions are radically different. Black holes are extreme laboratories for understanding the relationship between light, time, and gravity. They show us what happens when space-time curvature becomes so intense that even light, the fastest thing in the universe, can't escape. But there's more. Black holes might not be entirely black. In 1974, Stephen Hawking showed theoretically that black holes should emit radiation due to quantum effects near the event horizon. This Hawking radiation, as it's called, is incredibly faint for large black holes. For a black hole with the mass of the Sun, the Hawking radiation would have a temperature of about 60 billionths of a degree above absolute zero, far too cold to detect. But for very small black holes, if they exist, the radiation would be more significant. And over immensely long timescales, the radiation causes the black hole to evaporate, losing mass until eventually it disappears entirely. Hawking radiation is emitted as photons, among other particles. These photons carry energy away from the black hole, energy that comes from the black hole's mass, via Einstein's E equals mc squared. So even black holes, the darkest objects in the universe, emit light, at least in principle. And this radiation is pure quantum phenomenon, arising from the interaction of quantum field theory and general relativity, two of our most fundamental theories of physics. Light, even in the most extreme environments, remains central to our understanding of the universe. Let's take a moment to absorb all of this. We've explored black holes, where gravity is so strong that light can't escape. We've seen how light's path is bent by curved space-time. We've learned about Hawking radiation, the quantum emission of light from black holes. These are not abstract curiosities. Black holes exist. We've observed them. We've photographed them. The Event Horizon Telescope captured an image of the supermassive black hole at the center of the M87 galaxy, showing the shadow of the event horizon, surrounded by glowing light from the accretion disk. We've detected gravitational waves from colliding black holes, ripples in space-time itself that travel at the speed of light. Black holes are real, and light is central to how we observe and understand them. Now, let's zoom out even further. Let's think about light on the largest possible scales across the entire observable universe. Part 10. The cosmic microwave background, often abbreviated as CMB, is the oldest light we can see. It's the faint glow of radiation left over from the Big Bang, the moment when the universe began. About 13.8 billion years ago, the universe was incredibly hot and dense, filled with a plasma of particles. As the universe expanded and cooled, about 380,000 years after the Big Bang, it reached a temperature where electrons and protons could combine to form neutral hydrogen atoms. Before this moment, the universe was opaque to light. Photons couldn't travel far before scattering off free electrons. It was like trying to see through fog. But once atoms formed, the universe became transparent. Photons could travel freely. Light that was emitted at this moment has been traveling through space ever since. This is the cosmic microwave background, the light emitted when the universe first became transparent. When it was emitted, this light was in the visible and infrared part of the spectrum, hot and bright. But over 13 billion years, as the universe has expanded, the light has been stretched. Its wavelength has increased. It's been redshifted from visible light to infrared to microwave radiation. Today, the CMB is a faint microwave glow with a temperature of about 2.7 degrees above absolute zero. It fills the entire sky, coming from every direction, uniform to an extraordinary degree. We can detect this radiation with sensitive instruments. It's been mapped in exquisite detail by satellites like COBE, WMAP, and Planck. These maps show tiny fluctuations in the temperature of the CMB, variations of about 1 part in 100,000. These fluctuations are the seeds of all structure in the universe. The slightly denser regions became the first stars and galaxies. The slightly less dense regions became the voids between galaxies. The CMB is a snapshot of the universe when it was 380,000 years old. By studying it, we can learn about the conditions in the early universe, the composition of matter and energy, the geometry of space, and all of this information reaches us as light, photons that have been traveling for over 13 billion years, carrying information from a time when the universe was very different from today. From our perspective, these photons have been traveling for over 13 billion years. But from the photons' perspective, no time has passed. They were emitted in the early universe and absorbed by our detectors in the same timeless instant. This is the paradox we keep encountering. Light connects the distant past to the present from our perspective, but exists timelessly from its own perspective. The CMB also tells us something profound about the universe. It's remarkably uniform. No matter which direction we look, the temperature of the CMB is almost exactly the same, to within about 1 part in 100,000. This uniformity is called the horizon problem. Regions of the universe that are now on opposite sides of the sky were never close enough together in the early universe to have exchanged information, to have equalized their temperatures. And yet, they have almost exactly the same temperature. How is this possible? The leading explanation is cosmic inflation, a theory that says the universe underwent a brief period of exponential expansion in the first fraction of a second after the Big Bang. During this expansion, a tiny region of space, small enough to have been in causal contact, was stretched to encompass the entire observable universe. This explains the uniformity. Different regions of the sky are uniform because they all came from a tiny, causally connected region before inflation. Inflation is still a hypothesis. We have evidence supporting it, but not definitive proof. The CMB provides some of the strongest evidence, but the theory remains an active area of research. And at the heart of this mystery is light. The CMB photons carry information from the early universe, information that allows us to test theories about the universe's origins and evolution. Light is not just something we see. It's a probe, a tool, a way of accessing the history of the universe. Every time we detect a photon, we're receiving a message from the past. And the farther the photon has traveled, the older the message. Now let's think about the future. What happens to light as the universe continues to expand? Part 11. The far future of light. The universe is expanding, and the expansion is accelerating. This acceleration is driven by dark energy, a mysterious component of the universe that we don't fully understand. Dark energy makes up about 70% of the universe's total energy. It has a strange property called negative pressure, which causes the expansion of space to accelerate rather than slow down. If this acceleration continues indefinitely, the future of the universe will be cold, dark, and empty. Here's why. As the universe expands, galaxies move apart. Local groups of galaxies, bound together by their mutual gravity, will remain clustered, but galaxy clusters will separate, moving away from each other faster and faster. Eventually, trillions of years from now, distant galaxy clusters will recede beyond the cosmic horizon. Their light will be stretched to infinite wavelength and will become undetectable. Observers in those distant future galaxies will look out and see almost nothing, just a few nearby galaxies in their local cluster. Everything else will have receded beyond the horizon. Invisible, they'll have no evidence that the larger universe ever existed. The cosmic microwave background, stretched to infinite wavelength, will be undetectable. The galaxies we see today will be gone, beyond the horizon. They might conclude that their small cluster of galaxies is all there is, that the universe is small and isolated. This is called the cosmic isolation problem. It's a sobering reminder that what we can see is not all that exists, and that future civilizations might have access to less cosmological information than we do, simply because of the expansion of space. But there's more. Stars will eventually run out of fuel. The sun will exhaust its hydrogen in about 5 billion years, swell into a red giant, then collapse into a white dwarf. Other stars will follow similar paths. Eventually, all the hydrogen and helium in the universe will be processed through stars, converted into heavier elements, and locked up in stellar remnants. White dwarfs, neutron stars, black holes. New stars will stop forming. The universe will grow dark. The last stars will burn out in about 100 trillion years. After that, the only light will come from occasional collisions of stellar remnants, brief flares in an otherwise dark universe. Even this will fade. After about 10 to the 100 years, black holes will evaporate through Hawking radiation, leaving nothing but a diffuse gas of particles at nearly absolute zero temperature. The universe will approach a state called heat death, where entropy is maximized, temperatures are uniform, and no structure or organization remains. No stars, no galaxies, no light except the faint Hawking radiation from the occasional black hole remnant. This is the ultimate fate of light in our universe, if current theories are correct. But there's uncertainty here. We don't fully understand dark energy. We don't know if the acceleration will continue indefinitely or if it might change. The universe might evolve in ways we can't predict. And there's something profound to consider. We live in a special time, a time when the universe is transparent, when stars are shining, when galaxies are visible, when the cosmic microwave background is detectable. In the distant past, the universe was opaque. In the far future, it will be dark and empty. We exist in a brief window, cosmologically speaking, when the universe is illuminated and knowable. Light is abundant now. It won't always be. This makes our observations, our science, our understanding precious. We're documenting a universe that will someday be very different, very dark, very isolated, and we're doing it with light, with photons that have traveled across space and time, carrying information from distant places and distant times. Let's reflect on this. Part 12. Reflection. What we've learned. We've come a long way in this exploration. Let's take a moment to summarize what we've learned about light and why it matters. We started with the simple observation that when you flip a light switch, the room brightens. But we've discovered that this simple act involves one of the strangest and most fundamental phenomena in the universe. Light is both a wave and a particle. It exhibits interference patterns like waves, but comes in discrete packets like particles. This duality is not a limitation of our understanding. It's the nature of reality at the quantum level. Light has no mass, which means it must move at the speed of light. From the moment a photon is created until it's absorbed, it travels at exactly 299,792,458 meters per second. It can't move faster. It can't move slower. It can't stop. Because light moves at this speed, it experiences no passage of time. From the photon's perspective, the journey from emission to absorption, no matter how long from our perspective, takes zero time. The photon is created and destroyed in the same timeless instant. Similarly, the distance the photon travels is contracted to zero from its perspective. The universe, from a photon's point of view, is collapsed to a point. This timelessness and spacelessness are not poetic metaphors. They're literal consequences of relativity. Light exists at the boundary of space-time, at the limit where time stops and space contracts to nothing. Light defines causality. It's the fastest possible messenger, the cosmic speed limit. Nothing can travel faster than light, because if it could create causal paradoxes, allowing effects to precede causes. The speed of light is not arbitrary. It's woven into the structure of space-time, into the relationship between space and time, into the laws of physics themselves. Light is affected by gravity, not because it has mass, but because gravity curves space-time, and light follows the curvature. Near black holes, light can orbit or be trapped, unable to escape. The cosmic microwave background is the oldest light we can see, emitted when the universe first became transparent, carrying information from a time over 13 billion years in the past. And light will not be abundant forever. As the universe expands and ages, stars will burn out, galaxies will recede beyond the horizon, and the universe will grow dark and cold. We live in a special time when the universe is illuminated and knowable, and we learn about it through light. But beyond all these specific facts, there's a deeper lesson. Light teaches us that reality is stranger than we imagine, that the familiar things we take for granted are built on foundations that defy common sense. Time is not absolute, space is not fixed, causality is not simple, reality depends on the observer. And light, the most common phenomenon in our everyday experience, is at the center of all these mysteries. When you look at light, you're looking at the fundamental structure of the universe. You're seeing the threads that connect events, the messengers that carry information, the boundaries of what can be known. Light is not just illumination, it's revelation. It shows us not only what is out there, but how reality itself is structured. And that's what makes light so profound. It's both utterly familiar and utterly strange. We see it every day. But when we look closely, when we ask the right questions, we discover that it's one of the deepest mysteries in all of physics. Now, as we approach the end of this journey, let's ask one final question. What don't we know about light? What mysteries remain? Part 13. The remaining mysteries, despite over a century of intensive study, despite thousands of experiments and countless observations, there are still fundamental questions about light that we haven't answered. Some of these are technical questions about specific phenomena. Others are deep conceptual questions about the nature of reality. Let's explore a few of them. First, the measurement problem in quantum mechanics. We've said that before measurement. A photon is described by a wave function that encodes probabilities. Upon measurement, the wave function collapses, and the photon appears at a definite location. But what exactly is measurement? What counts as an observation? Does the universe really exist in an indefinite state until someone looks at it? Or is there something else going on? Different interpretations of quantum mechanics give different answers. The Copenhagen interpretation says that measurement is special, that it causes collapse. The many worlds interpretation says the wave function never collapses, that all outcomes occur in parallel universes. The de Broglie-Bohm interpretation says particles have definite positions all along, and the wave function guides their motion. We don't know which interpretation, if any, is correct. They all make the same predictions for measurable outcomes, so we can't distinguish between them experimentally, at least not with current technology. This is not just a philosophical question. It affects how we understand reality at the most fundamental level. Is the universe fundamentally probabilistic, with definite outcomes only emerging upon measurement? Or is it deterministic, with definite states at all times, and probability just reflecting our ignorance? Light, because it's a pure quantum phenomenon, is at the center of this mystery. Second, the nature of dark energy. We know the universe's expansion is accelerating. We attribute this to dark energy. But we don't know what dark energy is. The simplest explanation is that dark energy is a cosmological constant, a constant energy density throughout all of space. This fits the observations reasonably well. But the value of the cosmological constant required to match observations is incredibly small, about 120 orders of magnitude smaller than what quantum field theory predicts. This discrepancy is called the cosmological constant problem, and it's one of the biggest unsolved problems in physics. Why is the cosmological constant so small? Is there some mechanism that sets it to this value? Or is it random, different in different regions of a vast multiverse, and we happen to live in a region where it's small enough for stars and galaxies to form? We don't know. And this affects light, because the expansion of space, driven by dark energy, affects how light propagates across cosmic distances. It redshifts light, stretches wavelengths, and defines the cosmic horizon. Understanding dark energy is essential for understanding the universe's evolution, its fate, and the role light plays in connecting distant regions. Third, the relationship between quantum mechanics and gravity. We have two great theories of physics: quantum mechanics, which describes the behavior of particles and fields at small scales, and general relativity, which describes gravity and the curvature of spacetime at large scales. Both theories are extraordinarily successful. Both make predictions that have been confirmed to incredible precision, but they're fundamentally incompatible. They rest on different mathematical structures and different conceptual foundations. Quantum mechanics treats time as absolute and space as flat. General relativity treats time as relative and space as curved. At everyday scales and energies, this incompatibility doesn't matter. We can use quantum mechanics for atoms and molecules, and general relativity for planets and stars. And the two theories never overlap. But at the smallest scales, the Planck scale, about 10 to the minus 35 meters, both quantum effects and gravitational effects become important. At these scales, we need a theory of quantum gravity that unifies the two frameworks. We don't have this theory yet. String theory is one candidate. Loop quantum gravity is another. But neither is fully developed or experimentally confirmed. And this matters for light, because light is described by quantum field theory, which is a quantum mechanical framework. But light is also affected by gravity, which is described by general relativity. In most situations, we can treat these separately. But in extreme conditions, near black hole singularities, or in the very early universe, we need a quantum theory of gravity to fully understand how light behaves. Hawking radiation is one phenomenon that sits at the boundary. It requires both quantum mechanics and general relativity. And we don't fully understand it because we don't have a complete theory that unifies the two. Fourth, the nature of the electromagnetic field itself. We've said that photons are excitations of the electromagnetic field. But what is the field? In quantum field theory, fields are fundamental. They're not made of anything more basic. They're properties of space itself, potentials for particles to exist. But this is unsatisfying in some ways. It pushes the question back without really answering it. What does it mean for a field to be a property of space? What is space? Some theories suggest that space itself is emergent, that it arises from something more fundamental, like quantum entanglement or information. If this is true, then fields, including the electromagnetic field, are also emergent. But we don't know. We don't have a complete understanding of what fields are or where they come from. And this matters for light because light is a manifestation of the electromagnetic field. Understanding what fields are would deepen our understanding of what light is. Fifth, the role of the observer. We've talked about how measurement affects quantum systems. But what is an observer? Does it have to be conscious? Does it have to be human? Or can any interaction, any physical system that records information, count as an observation? This question touches on the measurement problem, but goes deeper. It asks about the role of information in physics, about what it means for something to be known or recorded. Some interpretations of quantum mechanics suggest that consciousness is special, that it somehow collapses wave functions. Others deny this, saying that any physical interaction can cause decoherence, the effective collapse of the wave function. We don't have a consensus. And this affects how we think about light, about observation, about the role of detectors and measurements in defining reality. These are some of the big questions that remain. But there are also smaller, more technical mysteries. For example, we don't fully understand all the ways light interacts with matter at the quantum level. We have good theories, but there are phenomena that are still being explored, like the exact mechanisms of photosynthesis at the molecular level, or the quantum coherence effects in biological systems. We don't fully understand turbulence in fluids, which affects how light scatters in the atmosphere, creating rainbows and sunsets and the blue sky. We don't fully understand the interior of the sun when light is created through nuclear fusion and then slowly works its way out through a dense plasma, taking thousands of years to reach the surface. These are details, but they remind us that even though we understand light very well in many contexts, there are always deeper levels of complexity, always more to learn, and that's as it should be. Science is never finished. Every answer leads to new questions. Every discovery reveals new mysteries. Light has been studied intensively for over 300 years. It's one of the best understood phenomena in physics, and yet it still holds secrets. It still surprises us. It still challenges our understanding. It still reveals new aspects of reality. And that's what makes it beautiful. Part 14, The Beauty of Light. We've spent hours exploring the science of light, the experiments, the theories, the mathematics. But there's something beyond the science, something that the equations don't capture. There's the beauty of light itself. Think about a sunset. The sky turning orange and red and purple as the sun dips below the horizon, the colors reflecting off clouds, creating patterns that are unique to that moment, that will never be repeated exactly. Science can explain this. The scattering of light by molecules in the atmosphere, the way shorter wavelengths scatter more than longer wavelengths, filtering out the blue and leaving the red and orange when the sun is low. But the explanation doesn't diminish the beauty. If anything, it enhances it. Understanding why the sky is blue makes the blueness more profound, not less. Think about rainbows, arcs of color appearing in the sky after a rain, each color distinct, perfectly ordered from red to violet. Science explains this too. Water droplets, refracting and reflecting sunlight, separating the colors by wavelength, creating the arc at a specific angle from the anti-solar point. But knowing this doesn't make rainbows less magical. It makes them more so. They're not miracles in the supernatural sense. They're natural consequences of the properties of light and water. And that makes them more wonderful, not less. Think about the stars, points of light scattered across the night sky. Some bright, some dim, some forming familiar patterns that humans have seen for thousands of years. Each one is a sun, like ours, burning through nuclear fusion, emitting light that has traveled for years or centuries or millennia to reach your eye. When you look at the stars, you're seeing the past. You're receiving messages from distant times and places. You're connected to the universe in a direct physical way. And this connection is made of light. Photons that left those stars long ago crossed the vast emptiness of space and entered your eye, triggering signals in your retina, creating an image in your mind. This is not abstract. It's real. It's happening right now, every time you look up. Think about the colors of the world: the green of leaves, the blue of the sky, the red of a rose, the golden yellow of sunlight streaming through a window. All of these colors are light, different wavelengths of electromagnetic radiation, distinguished by how they vibrate, how fast they oscillate. The green of a leaf is light that has been reflected by chlorophyll molecules, which absorb red and blue light but reflect green. The blue of the sky is scattered sunlight, filtered by the atmosphere. Every color you see is a message about the world, about what materials are present, how they're structured, how they interact with light. Your eyes are detectors. They capture photons and convert them into electrical signals that your brain interprets as vision, as the experience of seeing. The world you perceive, the visual world, is built entirely from light. It's photons entering your eyes, creating patterns of neural activity, giving rise to the rich experience of color and shape and motion. This is profound. Vision is not passive reception. It's an active process of construction, of interpretation, of meaning-making. And it's all based on light. Without light, there would be no vision, no color, no visual beauty. And yet light itself is invisible. You don't see light. You see with light. You see the effects of light interacting with matter, reflecting, absorbing, transmitting. Light is the medium through which the world reveals itself. It's the carrier of information, the messenger of form and color. And it's always been this way. For as long as there have been eyes, for as long as there have been living things that could detect light, the world has been revealed through photons. Evolution has shaped us to be sensitive to light. Our eyes are exquisitely tuned to detect photons in a specific range of wavelengths, the visible spectrum, from about 400 nanometers violet to 700 nanometers red. This range is not arbitrary. It's the range where the sun emits most of its light, the range that penetrates the atmosphere and reaches the Earth's surface. We see this range because our ancestors evolved under this sun, in this atmosphere, and those who could detect these wavelengths had a survival advantage. But there's more to light than the visible spectrum. Far more. The electromagnetic spectrum extends from radio waves with wavelengths of kilometers to microwaves, infrared, visible, ultraviolet, X-rays, and gamma rays with wavelengths smaller than atoms. All of this is light. All of it is photons, oscillations of the electromagnetic field, differing only in wavelength and frequency and energy. We can't see most of it with our eyes, but we can detect it with instruments. And when we do, we discover new aspects of the universe. Radio telescopes detect radio waves from distant galaxies, from pulsars, from the cosmic microwave background. Infrared telescopes see through dust clouds, revealing star formation regions. Ultraviolet telescopes observe hot stars and active galactic nuclei. X-ray and gamma-ray telescopes detect the most energetic phenomena in the universe: black hole accretion, supernova remnants, neutron star collisions. Each wavelength reveals something different. Each is a different window on the universe. And all of it is light. All of it is photons, differing only in energy. This is the unity underlying the diversity. Radio waves and gamma rays seem completely different. One has wavelengths measured in meters, the other in fractions of nanometers. One has low energy, the other high. One passes through walls, the other can damage DNA. But they're the same thing. They're both electromagnetic radiation. They're both photons, oscillations of the same field, the electromagnetic field. This unity is beautiful. It reveals a deep simplicity underlying apparent complexity. And it's not just aesthetically pleasing, it's practically important. Understanding that all these phenomena are aspects of the same thing allows us to predict new phenomena, to develop new technologies, to unify our understanding of nature. Maxwell's unification of electricity, magnetism, and light in the 1860s was one of the great intellectual achievements of human history. It showed that phenomena that seemed completely separate were actually intimately connected. And that unification continues to bear fruit. Modern electronics, wireless communication, medical imaging, all rest on our understanding of electromagnetism, on the unity of the electromagnetic field. Light is not just beautiful in an aesthetic sense, it's beautiful in a deeper sense. It reveals patterns, connections, unities that aren't obvious from casual observation. It shows us that the universe is comprehensible, that beneath the apparent chaos and complexity, there are simple, elegant principles. And it shows us our place in that universe. We're made of matter, of atoms and molecules, but we experience the world through light. We're bathed in it, shaped by it, connected to distant stars and galaxies through it. Light is the bridge between us and the cosmos. It's the medium of connection, the carrier of information, the revealer of truth. And it's always here, always present, always ready to teach us something new if we pay attention. Closing. A gentle ending. We've reached the end of our journey through the nature of light. 3 hours of exploration, from the familiar to the strange, from the everyday to the cosmic. We've learned that light is both a wave and a particle, that it has no mass, that it moves at the cosmic speed limit, that it experiences no time, that it defines causality and connects events across space. We've learned that light reveals the universe to us, from the nearest candle flame to the most distant galaxy, from the cosmic microwave background to the event horizon of a black hole. We've learned that light is deeply mysterious, that despite centuries of study, we still don't fully understand it, that it sits at the intersection of our deepest theories and our most profound questions. And we've learned that light is beautiful, both in its phenomena, sunsets, rainbows, stars, and in its underlying principles, unity, simplicity, elegance. But more than any specific fact, I hope this journey has given you a sense of wonder, a sense that the universe is stranger and more beautiful than everyday experience suggests, that the familiar things around us, when examined closely, reveal depths we never suspected. Light is everywhere. It's the most common thing in our experience, and yet it's one of the deepest mysteries in physics. That paradox is itself profound. The universe doesn't hide its secrets in remote corners, accessible only to specialists with expensive equipment. It puts them right in front of us, in plain sight, in the everyday phenomena we take for granted. All we have to do is look closely, ask questions, follow the logic. Let the strangeness reveal itself. And when it does, when we see that light doesn't experience time, that it exists at the boundary of space-time, that it defines the structure of causality and the limits of knowledge, we're seeing not just facts about photons, but truths about the universe itself. We're seeing the machinery beneath reality, the gears and springs and levers that make everything work. And that's what science is, at its best. Not just a collection of facts, but a way of seeing, a way of looking at the familiar and finding the profound, a way of asking questions and following them wherever they lead, even if they lead to places that seem impossible or paradoxical or strange. Light has led us to all those places, to wave-particle duality and quantum mechanics, to relativity and the nature of time, to black holes and the cosmic microwave background. to questions about reality, observation, causality, existence. And through it all, light has been both the subject and the tool, the thing we're studying and the thing we study with. When you look at a star, the light entering your eye is both the message from that star and the medium that carries the message. The photon is both the information and the carrier of information. This dual role is fitting. Light is so fundamental that it can't be separated from the act of knowing. We know the universe through light. Our knowledge is built from photons, organized in our minds, creating models and theories and understanding. And yet the universe existed before there were minds to know it. Light was traveling through space long before there were eyes to see it. The cosmic microwave background has been propagating for over 13 billion years, most of that time with no observers anywhere to detect it. The universe doesn't need observers to exist, but observers need the universe, need light to know anything at all. This asymmetry is worth contemplating. We're part of the universe. We're made of the same atoms as stars and planets. We're subject to the same laws of physics. And yet, we're able to step back, to observe, to understand, to wonder. We're the universe becoming aware of itself. Atoms arranged in such a way that they can ponder their own existence, can ask questions about origins and futures, can trace the paths of photons from distant galaxies to our retinas. This is extraordinary when you think about it. Extraordinary and humbling. We're small. Our lives are brief. Cosmically, we're insignificant. We exist for a blink in a universe that's 13.8 billion years old and will last for trillions more. But we're also connected through light, through gravity, through the atoms in our bodies that were forged in stars. We're part of a cosmic story that spans from the Big Bang to the far future. And we're aware. We can look up at the night sky and understand at least partially what we're seeing. We can trace the journey of photons from distant stars. We can build telescopes and satellites and detectors to capture light from across the electromagnetic spectrum. We can decode the messages carried by those photons, learning about the composition of stars, the expansion of the universe, the nature of space and time. This is a gift. The universe is comprehensible. It follows laws. It reveals its secrets to patient observation and careful reasoning. And light is central to this revelation. It's the primary messenger, the carrier of information, the link between there and here, then and now. So the next time you see light, sunlight streaming through a window, a lamp illuminating a room, stars dotting the night sky, take a moment to appreciate what you're seeing. You're seeing photons, massless particles that have traveled at the speed of light, experiencing no time, connecting events across space. You're seeing the messengers of the cosmos, the threads that weave the universe together. You're seeing one of the deepest mysteries in physics, something that's both completely familiar and utterly strange. And you're seeing beauty, not just the aesthetic beauty of colors and patterns, but the deeper beauty of underlying principles, of unity and simplicity and elegance. Light is all around you. It's been there your whole life, and it will be there revealing the universe for as long as you care to look. So look, wonder, ask questions. Let the strangeness wash over you. And remember that the universe is always more interesting, more mysterious, more beautiful than we imagine. That's the gift of light. That's what it shows us, if we pay attention. Rest now. Let these ideas settle gently. Let the wonder of light fill your thoughts as you drift into sleep. And when you wake, when you see light again, perhaps you'll see it a little differently. Not just as illumination, but as revelation. Not just as brightness, but as connection to the cosmos. The light is waiting. It always has been. Thank you for this journey. Sleep well.